Welcome to tutorial 7, where once again we take a further step into the world of pointers and memory, and now dealing with dynamic memory allocation. And so you've dealt with memory allocation before, which is more at runtime, like when you've declared your variables, like right here, that are local. The idea is, well, you know that this is in the main, so this is going to be saved here, like created when the mains started as a local variable, and then when the main finishes it disappears. But sometimes now when you're running programs, you need to actually allocate or request more memory from the actual system, so your operating system, so you can do work with it. And so this is your first lab to get a little bit of practice of dealing with the keywords of new, which is used for allocating memory, and then delete, which is deallocating and giving back memory to the actual system. So something that's required in C++. So to start with, for question 1, we're going back to that funny coding or funny sorting method that we completed previously for right now. Now this one here started originally that we had pointers and we were working with them, but we didn't dynamically allocate memory or do anything. We were just referencing variables we wanted to work with. So what we're going to do here is now just show a small baby kind of example of allocating actually memory. So there's a wider range of uses you'll have for this, like when you go to linked list and you need to dynamically allocate memory to build larger lists as the program runs when you don't have a predefined size. But here we're just showing an example of just how to allocate memory and how to deallocate it. So for part 1 here, we're supposed to actually remove the original integer variables and then use the new keyword to actually initialize new memory, so dynamically allocate memory for the small, medium, and large reference variables. And then before we call our original funny sort that we had before that's going to work with pointers to memory, we want to actually ask the user to enter the values. And then once we're done, we want to actually deallocate the memory, saying that we are done using it. So to start with, 1, get rid of those original variables that we had. Step 2, allocate some memory. So get rid of the variables here where we were just getting the variables and getting their memory address. Now we want to allocate memory. So it's always new and then the type that you want to allocate. So we want this small pointer to hold a reference to some dynamically allocated memory, and so it's going to create one chunk of size int. If you want to do doubles, well, you'd have to have different pointers to hold it, but you go new double. So it's always new space the type you want to actually allocate. And so you can also allocate arrays dynamically, so there'd be a new int, and then you'd be like, okay, 10. So I'm creating an integer array of size 10 and dynamically allocating that. But here we're just making 3 ints. Now automatically what you're going to have to keep track of is if you are allocating memory, you have to deallocate it at the end. You won't get any compile errors warning you about this. It'll actually run. This is more semantical. But what happens is if I keep allocating memory, you've marked it in the system saying, hey, I'm using this memory. And so if you don't deallocate it when you're actually done with it, the actual system for your process will think, hey, that's still in use, and so we'll just leave it there. And it's called a memory leak. Now, once your process stops running, things will be cleaned up by the operating system. But say if you had your program running for a very long time, this would keep up taking more and more memory. And remember, you'll learn later on, but when your programs are running and we say the words memory, right now you can visualize it being RAM. Like that's your RAM. So these are programs that keep taking up more and more RAM the longer they're running and leaving what's called a memory leak. So you just have to remember that whatever you're doing with allocating memory, when you're done using it, you should be deallocating it. So even though that's step 4 in tutorial, I'm automatically going to go do this. That I know all the code that's in between here, so the printing and everything else is going to be working with these variables, but I know right here before we exit the main, I am done using it, so I want to deallocate it. So you just use the keyword delete, and you give it the actual memory address to delete. Now this has got to be memory that's been dynamically allocated, not some other variable you're working with, and so that it's not null or anything like that. So we know that we've created these as ints, so I'll just say delete, and I know that by the end here each of these pointers is holding some dynamically allocated memory, so I'm indicating the system that I am done and they can be reused and not having any bad memory leaks. Next, we've got to keep updating the program, so I'll take out that output that I originally had to output the original X, Y, and Z variables, and we're just doing the outputs of dereferencing the actual pointers we have and going to that dynamically allocated memory. Now before this, we need to read in some data. So first off, make sure I have IOStream up here in the namespace. And then down before we call our funny sort, just get the user to enter some data. Now the idea is here, when I read the data in, I want it to be stored into that dynamically allocated memory. So I need to dereference the actual pointer. Because if I just did this, it's going to try overriding or causing issues into the actual pointer that's stored here. By putting the star, once again, I'm saying dereference this pointer, which will be going to that dynamically allocated memory. Okay, so we've got those three steps. We've got our allocation. We are reading the values in and making sure it's being stored into the allocated memory. So using the pointer that we desire and dereferencing it, so it gets stored into it. Calling our sort that takes the pointers and shifts everything around, so manipulates stuff in that dynamic memory. And then we output the actual values, making sure once again to actually dereference the actual pointer. And then now that we know that we're done with everything, then I will delete that memory to say that, okay, it's actually marked to be reused by the system and not leaving a memory leak. Boom, no errors. We can test this here, some original values, let's say like 10, space 3, space 2. And there we go, 2, 3, 10. We can run it again, do like 1, 2, 3. How entertaining is this? Okay, so we have it working. So that's that first part. So just remembering that you're using the new word to allocate memory, specifying the actual type that you want to allocate from the system, and then it gives you back. This results in an actual memory address that's getting stored into this pointer. We are then, when we dereference this, is going to that memory that's right here and doing the rest of the work. Okay. Now we go on to question 2. Now this one here is a lot more of tracing code, but just noticing when there's error and making sure once again we're going back to our actual diagrams that we had before, so our drawing diagrams. So I will once again open up OneNote to do a few of these. Okay, so we'll go with that very first one that we have. So you can see here we have this code here where it's doubling, making the pointers and allocating some actual memory, dereferencing and doing some actual work. And so there's some errors here, so we need to go through actually drawing this and figuring out, well, okay, well, what's going wrong? Go past all that old stuff and get ready for my horrible drawing doing this on a screen. So one, we have that first line right here of creating the actual two pointers. They start out being null, so not referencing anything. Next, we're allocating one double variable, and that address is being stored into PD1, and then the same thing for PD2, so new memory. So when we have the first new line, new memory is going to be allocated. We have right here. The address is then going to be returned and stored into our pointer. So drawing the arrow saying that's saved there. The second line, we get the new here again. And we're doing this. And so we should be seeing deletes of these later on, but we keep following the code. We have star PD1s, which means dereference it and go to the actual memory and put 100 in it. So we're right here, follow over here, and put 100. And then we say PD equals PD1, and the key thing here is that there's no star, so we're not dereferencing, so we're actually copying the addresses that are here. So that means PD2 then is now referencing up to here, and we have an issue. We didn't allocate this memory. There is no arrow being drawn to that, so that's a memory leak. That is now lost past this point. So when we go to do PD1.delete, that's going to follow the arrow here and go over, and it's going to delete this 100 that we have right here. So it's going to mark it. When we go to delete PD2, that's also going up to here, but this has already been marked for actual deletion. So that's an error. It's already been deleted. We don't need to do it again. But we have this other case where we didn't keep the reference. And this is very important when it comes to dynamically allocating memory, is we don't have a variable name to it anymore. We just have the address, and that address has to be stored into a pointer. And so we need to, if we're done with that memory, you want to get rid of it, we should delete it, and then we can set that pointer to null. But we can also have to worry about that, like if we move a pointer to a different piece of memory, then, well, we lose that other one. It loses it away. It's like holding on to a balloon, a helium balloon on a string, and then you let it go and it just floats away and you're never getting that back. So that issue here is that we are making it equal to it right here, and then we're trying to delete the same piece of memory twice, and we never deleted the actual original memory we had for the actual double. Okay, let's go on to the next one. So here we have two integer pointers to start with. And both start out at null. Next we're going ptr1 equals ptr2. So this just means copy the address that's currently in ptr2 and put it into ptr1. When we look here, ptr2 is null. So null gets copied over and nothing changes in our diagram. The next line here is then allocating a new piece of memory, so that new int. So we get a new piece of memory that's actually allocated, and then the address for that saved into pt2. So that's over here. We are then reading in right here of cin star ptr2, so we dereference this and go this, so follow the arrow, go over here, and the read in value, so whatever value is read in is put into there. Next we go to ptr1 and we dereference it, but this is null, and you can't dereference a null point, so crash. Yeah, blah, 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 blah. Like you can't even do that. And then afterwards we do delete ptr2. So, well, whatever, that's fine, but we would have never made it there because it would have crashed right there at that line. Okay, next one. So again, we start off with 2, so we're doing this one down here at the bottom now. Let me increase that since this is... We're working on this one right here. So we're starting, and we have 2 pointers again. They're both null in the very beginning. Then we have ptr1 equals new int, so new piece of memory allocated. ptr2 equals ptr1, so it doesn't duplicate the memory, it copies the address. There's no dereferencing or stars here. So ptr2 references up to the same thing that ptr1 is currently referencing. We cin right here to ptr1, So dereferencing, because we've got the star, so follow the arrow, go here. The value will be stored into that. So currently both of these are pointing to the same thing, and if we printed them out, we'd get that. We now do a delete of PTR2, which then means take whatever address is, so it means this memory here gets deleted or marked for deleting, and later on we're trying to dereference that, and maybe it worked, maybe it wouldn't. Say it's marked by this system, and so we shouldn't have this. Like we have the original one and we've deleted it, that same piece of memory, but then we're trying to access it again. It may be two different pointers, which are fine, we still have these, but the memory that they were referencing, which is both the same, is not there. So it could run and pull up some random values, or it could be marked by the system that, hey, that's not there anymore. You don't know, so you have to be careful of what order you actually go through. Okay, now this one is a little bit larger. So you have a function called gimme. You have the main, so boolean done equals false, while not done, done equals gimme, and then exiting. Going into gimme, we have bool, and here we can see we got a pointer, and we're dynamically allocating an actual double. We are reading the value in and storing it into that memory, so this is still all legal so far. We are outputting what was done here, so this star, and then we're going done equals dereferencing if it's less than 0, so it's a Boolean expression. So if the result that's in that dynamic memory is less than 0.0, then done is set here, and going to here. And you're like, looks okay. Like this would actually compile, this would run, this wouldn't crash, but there's an issue. Can you see it? And you're like, oh, look at this entire program. Look here, we've allocated memory. Do you see delete anywhere in here? You're like, okay, well, we have this here. This dyn is never returned or given back to anyone, so the address that was dynamically allocated is not given anywhere else, and so its only life of existence is within this method. And so if it's been allocated, we've got to deallocate that when we're done. And so like after this done statement, we're done working here, we should actually have a delete dyn. So this will not crash a program. This will not cause a syntax error or any kind of semantical thing, but it'll cause what's called a memory leak. And so you should have an actual delete. Now this one, we have an integer x, and we have a pointer p. So let's go through tracing this a little bit and see what's going on in the actual memory. So first off, we have the variable x right here. We have a pointer right here that's pointing to null in the beginning. After the C, we have a cout entering a number. They will enter that value. Put a v here to say that be stored into x. Then we're checking if x mod equals 2, so it's right here. P equals ampersand x. So right here it could be like if it goes into the if, it means that, okay, the pointer is referencing this variable, which is a local variable that was not dynamically allocated. If it doesn't go into the actual if, it goes to elsewhere, yes, now we get a variable that's actually allocated. So we get some memory that's dynamically allocated and stored here, and the results of x plus 1 is stored into that memory location. Then after that, it prints out the value for x and dereferencing the actual pointer right here, and then it goes delete p. You're like, seems okay, I can see a new right here, I can see a delete, but there's an issue. Like if we go through here and we find that it's going to go into the else, we'll allocate memory, we'll come out, we'll deallocate it. So that's good. We would get rid of the memory that we actually made right there. But there's a problem. What if we go into the if right there? It means that this p, the pointer, is referencing x, which is not, this is not dynamically allocated. And so we go down to the delete, that's going to cause an issue, if not crash the actual program, because you're trying to delete a local variable that was not dynamically allocated, creating the actual new statement. So this is the issue, is that if you have a pointer to something, you should be careful if you're calling delete that this is to a piece of dynamically allocated memory, not some local variable memory. Okay, well, look at that. Only a 20-minute tutorial right here. Now I do suggest go through this, play around with allocating some memory, get used to these things. This will be really important. And just remember the key things of allocating memory using new. You should always have a delete at some point in time to delete that allocated actual memory. So it doesn't need to be like the same pointer holding that, just the same address to the allocated memory, even if it's been passed around. But you need to have that delete. You also need to be careful what you're referencing. So when you go to do a delete, that is not local actual data. And the actual ordering that you're working on. So as we worked here, that we don't have any memory leaks where you lose track of memory and you don't delete it before moving a pointer reference and you lose track of it completely. Or if you're trying to delete a piece of memory twice. Or right here where you're actually already deleted it and trying to access it after deleting it. And then this one here where you just actually dynamically allocate memory, but then you never actually give it back, which again, this is an infinite loop for done, and so this could cause a memory link the longer the program runs. And the actual last one where you could potentially have a case where you're trying to delete some actual local memory. So there you go. Shorter tutorial, I know as this semester gets busier. But as always, I hope that you're doing great and that I remember that you're awesome. And if you're having, again, difficult times in the course, reach out for help. But also if you're having difficult times in life, remember to try to reach out. If nothing else, there are resources on campus or other people like myself or other teachers who could guide you to them if you need help. If nothing else, try to reach out to a friend. You never know. And if you're doing okay, maybe try to reach out to a friend you haven't heard from in a while and just to say hi and check in and see how they're doing and just maybe put a smile on someone's face and make this world a little bit better through the little actions that we can do that build up to potentially larger, better, wonderful things. Just like the better, wonderful, amazing people that I know all of you to be. Okay, go on, and I hope you have a wonderful day.